So the idea of linearizing is something that we went through several times, and I think if people are honest, it's something that didn't come easily as we learned it, and I, presented it in a certain way, and we tried it different times, and with my help, I think most people could work their way through it, but I'm not sure it ever really came naturally. So I saw a different approach when I was watching some of the AP review videos, and I'm going to throw it out as an alternative. It's not as useful because it doesn't work every single time, but it works probably almost every time. And it's probably likely that you'll see something like this on the AP exam this year. They keep kind of emphasizing the lab focus, and linearizing is definitely part of a lab experience. So I want to show you the alternative, and I'm going to let you choose whether that makes more sense or whether my approach makes more sense. And I'm going to kind of show you both just to remind you of what mine looked like. And then you can kind of decide. So the idea of linearizing is this. When you're taking measurements of a dependent variable versus an independent variable, so you're changing one thing, the independent, and then something else changes as a result, that's the dependent. And then you plot it. Sometimes you're lucky and it comes out a perfect line. And typically the slope of that line contains some sort of important physical parameter. But other times, it doesn't come out of line. But that parameter is still kind of wrapped into some other feature on the graph. So linearizing is sort of the process of taking data that would be like this, and maybe comes out, a curve, or a curve like that, or, maybe, I don't know, something like that, something that's not a line. And we transform the data. We plot something a little different here and here, some different version of y and x, so that we do get a straight line, okay? And with any real data, this is going to be, roughly a line. It's not going to be a perfect data. So let me show you an example that we did back in the mechanics semester in a lab, one of our little virtual labs, and I'm going to do it using both approaches, and you can see which one you like. So as part of the gravitation unit, when we studied orbits, I had you do this virtual lab where you looked up the periods of the different planets around the sun, and you plotted that against the orbital radius that each one has. Now this is a terribly scaled drawing, but what's nice about it is you can see all the planets nicely. So it turns out that the period, the amount of time it takes to orbit once, is related to how far each planet is from the sun. Okay, but when you plot that, the period versus the radius, it comes out curved. So we wanted to linearize that data, and what we were after was the physical parameter of the mass of the sun. Okay, so I'm going to kind of take you through that using both approaches, the one that I showed you before and this new one, for you to decide which one you like better. So in either approach, we need to have the equation that relates the period of an orbit with the radius of that orbit. So that comes in lots of different forms. I think the form I probably remember the best is the one that's just solved for the period, because for all of our period equations, they all had the similar feature that they had 2 pi and then the square root of something. And in this case, for an orbit, it is the cube of the orbital radius divided by g, the gravitational constant, and the mass at the center of all of the orbits. In this case, that would be the mass of the sun. So that's what we were kind of after. Okay. So where you go from here is where the two approaches differ. My style was, I wanted you to think, I'll kind of show the McManus style here. I wanted you to think in terms of the equation for a line, y equals mx plus b. And I wanted you to format this so that it could look like that. So whereas we have our dependent variable y typically in front, we want our equation here to have the same thing. Well, it's already got that. So we've got t. But what was different here is we wanted the variable x, the thing we're changing, in this case it's r, to be kind of separated next to all of the other fixed parameters. Okay, so we didn't want them kind of all mixed up into what looked like one expression, we want them kind of separated with just, a little multiplication in between. So the trick was you just separate this square root, so we could have the 2 pi and then the square root of g and m. Okay, so all I did was I moved this part over here to be under this part because those are all the fixed parameters. And then everything that's left is up here in the numerator, the square root of r cubed. Okay, so now what we have here, oh, and I guess we have plus 0. But we have something that looks like it's in the same form as our familiar y equals mx plus b. So it would tell you what to plot. Whereas we typically plot y, we're plotting t, and we would typically plot x, we're plotting this, the square root of r cubed. And then the slope of that, once you find that number is equivalent to everything here, which would be 2 pi over the square root of g and the mass of the sun. And then you could solve for the mass of the sun. Okay? So here's a different style. And again, this is in one of the videos, the one that I referenced on the little spreadsheet. It's the same idea, except instead of writing it this way, you write something basically like you learned in Algebra 1, the definition of slope, which, now algebra teachers would hate this, and there's something in me that hates this as well. Oh, that was nice. And that is, it should be delta y and delta x. So that's why this has a limitation on it. The limitation is this only works if this graph goes down through 0, 0, down through the origin. Okay, which this one will, because if you don't have a radius, you also don't have an orbital period. So what you do here is the slope is all your fixed parameters, and then y and x are your two variables. Okay, so you algebrate this equation so that it's in this form. So we can leave t over here where it is, but what we're trying to do now, let me write it a little bit differently. Let's have t over here on the right side, just so that it looks like this. And then the other variable, which is this, we need underneath it. Okay, so what we're going to do then is just divide both sides by the square root of r cubed. And all we're doing here is Algebra 1 level stuff. We're just rearranging this equation so that we separate things. So the two variables are here, and what's left over here is the 2 pi, the square root of gm, okay? So again, this and this, totally equivalent. But what you see now is this correspondence where if you plot t where y normally goes, and you plot this where x normally goes, you have a slope that's equivalent to that. Again, exactly the same as what I had over here, right? Just a different form, kind of getting all your parameters to be on one side of the equation that are fixed, and all the two variables in a fraction form on the other side of the equation, all right? So let me do one more just to show you the distinction, and then we'll kind of leave it at that. I'll make this one go a little bit quicker. So suppose we want to measure the value of little g using a series of ball drops. So we just drop a ball from a certain height, and we measure how long it takes to hit, because that relationship is related to the measure of the strength of gravity here. You actually did something like this in Physics 1, depending on whose class you were in, but you just did one measurement rather than a series. But if we were to do this, just imagine making a little t-table here where we have different heights, and then we measure different times, okay? And then we have a whole bunch of numbers, and then we plot it. Well, if you plot this, you're not going to get a line. And so in order to figure out what the line should be, again, you need the equation that relates height with time, okay? Well, that comes from one of the kinematics equations for uniform acceleration, which looks like this. I'm going to write it in a slightly different form. The change in y, because we're talking about vertical motion here, v naught yt plus 1/2 at squared. Okay. Now, if we start the ball from rest and we just drop it, then this initial velocity term goes away. Okay. If you can't do that, then the other system of writing the equation is not going to work. Okay, because a delta y will not be the same as a y, and so that's again sort of a limitation. So I'm going to get rid of the delta now. So here's the equation that relates those two things. So in this new style, if you write it in the form of slope is y over x, again, look at your equation, collect all your variables on one side. Well, in this, it's y and t squared. Okay, so we can put the y here, the t squared there. And what is the rest of this equation if we have that? It is 1/2 of a. Okay, so now the slope of a graph of y versus t squared will give us 1/2 of a. Okay, I think my dog loves this derivation. Can you hear how exciting it is? So y t squared, series of dots, probably wouldn't be very good data. Plot the best fit line through there, kind of hit the average, some above, some below. Don't go too steep, too shallow, and that slope is half the acceleration. Okay, so again, just a different variation on the idea of linearizing that I described to you before. So food for thought, but I would expect something related to linearization. And if it's something you want to talk through more with me before we get to exam day, that's absolutely a great thing to do. We can take you through some practice with that. So, all right, that's going to do it. Thanks for watching. Hopefully that was helpful for you.